Okay, this little video is about general 3D rotation matrices. Okay, what do we mean by that? Let's say we have some reference frame, 0 like so, and we have a new reference frame like so, that's oriented in some non-simple way. In other words, it's not a pure rotation about one of the three axes. So this is reference frame 0, and this is reference frame, this is frame 0, and let's call this frame 1. Okay, so we have a general rotation, i.e. not necessarily along one of the coordinate axes. One of the three coordinate axes. What is the relation? Or rotation matrix connecting EX naught, EY naught, EZ naught on the one hand, and EX1, EY1, EZ1 on the other hand. Okay. So to derive this relationship, or to understand what this relationship looks like, just think about the following thing. Say we have some vector v. It could be a unit vector or it could be a non-unit vector. Then the vector v can be written in the frame 0 or the frame 1 as follows. For instance, we can write it in terms of frame 0 as something times EX0 plus something times EY0 plus something times EZ0. Okay. Now what are these somethings? This is the component of V along EX0, or another way of saying it is the projection of V onto the vector ex0, that's actually going to be equal to v dot ex0 by definition. So we can write the vector v, any vector v, as v dotted with ex0 plus v dotted with ey0 plus v dotted with ez0. Okay, so where does this come from? This is just what you learned in your sort of early undergrad or high school perhaps, where you have some vector v and some unit vector n, then the projection of v onto n, let me draw it slightly exaggerated. So v is like so. The projection of v onto n, this quantity, is basically v dot n. Okay, it's the component of v along the unit vector n. Okay, where this v is any vector and this is a unit vector. And this is the component of v along n. Okay, so this is what we have. We have some vector v equals the component of v along ex naught, which is v dot dx naught, component of v along ey naught, which is v dot ey naught, and so on. Okay, so this equation allows us to essentially represent any vector v in terms of ex naught, ey naught, including the vectors ex1, ey1, ez1. Okay, so let's do that. So using this equation with ex1, ey1, ez1 instead of v, we have ex1 equals essentially ex1 dotted with ex naught. So we are replacing v with ex1 right now, plus ex1 ey naught plus ez1 dot ey naught, ez naught. Similarly, we have ey1 equals ey1 dotted with ex naught ey1 dot ey naught plus ez1 dot not ez1, we're doing EY1 right now. E Z naught. Really, this is how I should have written this. EZ1 equals something that EX naught plus something that EY naught plus something that EZ naught. The something is basically EZ1 dot EZ1 dot EZ1 dot, and this is EX naught, EY naught, EZ naught. Okay. Okay, so that's the relation. Those are the three relationships that we have, which is, like we said, essentially using this relationship with EX1, EY1, EZ1 instead of V. Now, we can again write this in terms of a matrix relationship. And the matrix looks like this. It's again a 3 by 3 matrix. It's EX1 dot EX naught, EX1 dot EY naught, EX1 dot EZ naught, and then EY1 dot EX naught, EY1 dot EY naught, EY1 dot EZ naught, EZ1 dot EX naught, EZ1 dot EY naught, EZ1 dot EZ naught. Okay, so that's a 3 by 3 matrix, and of course we are trying to write EX1, EY1, EZ1 in terms of EX naught, EY naught. EX naught, EY naught, EZ naught. Okay. So this is the rotation matrix now. There's a 3 by 3 rotation matrix. Right, so where each of these is a scalar, a dot product gives you a scalar. It's a 3 by 3 rotation matrix. And this is a rotation matrix that takes EX naught, EY naught, EZ naught to EX1, EY1, EZ1. Okay, so given these three vectors, you get these three vectors. So it takes you from 0 to 1 is how we are going to say it. So we are going to denote it by R0 to 1. Okay, notation. For this matrix. So it's a 3 by 3 matrix. Now we can write it as EX naught, EY naught, EZ naught. Sorry. EX1, EY1, EZ1 equals R0 to 1. EX naught, EY naught, EZ naught. And if you sort of follow the mechanics of matrix calculus or matrix algebra. This you can sort of pre-multiply both sides by the inverse of R01, and of course you have so the inverse of that times R0 to 1 times EX naught, EY naught, EZ naught. Of course, this gets us an identity. So what we have is R0 to 1 inverse EX1, EY1, EZ1 equals, these two things cancel or give you identity, and we get equals EX naught, EY naught, EZ naught. But by definition, we have, if you have some relationship like this, of R matrices, we have, so if you have some matrix that goes from these unit vectors from the one coordinate frame and give you unit vectors in the 0 coordinate frame, you should call that matrix R1 to 0. That's the way we've defined notations. So if you compare these two relationships, of course, we have R1 to 0 equals R0 to 1 inverse, which makes sense. Okay, R1 to 0 is R0 to 1 inverse, and R0 to 1 itself is this matrix of dot products. Okay. Okay, so what have we done? Very quickly, we just defined the notion of a general 3D rotation matrix. We wanted a matrix, a rotation matrix that related some set of unit vectors to some other set of mutually orthogonal unit vectors. And we essentially derived a relationship based on essentially projection of one set of unit vectors onto the other set of unit vectors using this relationship using dot products. And we got this relationship for the rotation matrix that related any two axes sets, coordinate axis sets or reference frames. In the next video, we shall look at the properties of these rotation matrices.